I would like to introduce our moderator, Dr. Sampathkumar. Dr. Sampathkumar is the Head of Center of Excellence, Digital and Operation, Biocon Group. He is having 25 plus years of experience with roles held in quality control, quality assurance, process development, regulatory, and manufacturing. He holds a PhD and MPhil Chemical Engineering from the City University of New York. I request Dr. Sampathkumar to introduce our panelists and speakers.
Good morning, everyone, and thanks to ICT for organizing this event and giving this opportunity here. It's a pleasure to be here, and ICT has lined up a number of esteemed speakers for you, and the topic about process analytical technologies is actually a lot of spoken topic. It's a very upcoming topic. A lot of companies might not have adapted fully, but so you have to learn from these experts, maybe how to adapt that in a company in a manner that it can increase productivity as well. So, Dr. Anurag will be presenting a topic on model-based control of continuous bioprocesses, and that can accelerate process development and enhance productivity. And Dr. Janice's presentation is also going to be related to PAT. She will add some more success stories related to PAT with the application of multivariate modeling approach for the adoption of Raman spectroscopy for monitoring and control in mammalian cell cultures. And Mr. Anshuman will be presenting on cloud computing for data-driven biomanufacturing in the Industry 4.0 paradigm. So the topic is next generation PAT, data analytics, and Industry 4.0. And the last presentation topic would be on cutting-edge informatics solutions and data analytics by Dr. Manish to help make data-driven decisions and accelerate biosimilar development. So each presentation will be for 15 minutes and followed by a panel discussion with the speakers. So if you don't mind, you can write down your questions and then you can reserve your questions for the panel discussion so that we can be on time. So now let's get going with the first topic, model-based control of continuous bioprocesses by Professor Anurag Rathore. Dr. Rathore has obtained his PhD from Yale. At present, he is a professor at the Department of Chemical Engineering at IIT-Delhi with research in the areas of bioseparations, process analytical technology, quality by design, computational fluid dynamics, multivariate data analysis, and he has 25 plus years of experience with process development, scale-up, technology transfer, validation, multivariate data analysis, PAT, and QBD. Professor Rathore is also associated with scientific startups as a technical advisor. And his pet peeve and hobby includes managing his personal finance. So other than PAT, you can talk to him about how to manage your personal finance as well. So let's welcome Professor Rathore. Please give a round of applause.
Okay, thanks to Partha and thanks to Ratnesh for organizing this event. Slides. Okay, so the topic that I was given is basically on model-based control. Continuous processing, I think, as you know, is increasingly being implemented already in a big way, particularly in the US and Europe. And I think for now the Indian companies as well are kind of delving into it, so it's something of interest. And process control for continuous becomes important, right? Because you don't have the flexibility to wait and see the outcome of one step before you decide what to do with the next step. So this is kind of how the continuous process platform that we have looks like. We have your bioreactor. Let me try if this works. No, it doesn't. This is not working. No. It's okay. So basically, a bioreactor, acoustic wave separator for clarification. You can also use depth filtration or microfiltration if that's what you want. Surge tank, then for continuous chromatography, we are using Biosimilar. We have a patented, innovative operation called coiled flow inversion reactor, which we are using for viral inactivation. Then Biosimilar again, and then your UFDF. That's kind of the platform we have. Now the question is that, all this is fine, but what happens if you have a problem, right? Because when you're running continuous, your response time is very limited, right? Because if you don't respond very quickly, then it's going to derail your process. So every time you'll be starting the process and then kind of ending the process abruptly, restarting the process and so on, right? Which obviously cannot do. So the question is, how can I respond? And these are all the stuff you can see in the red are basically different attributes that you normally worry about at different steps, right? So you can imagine that if I have this process running in the plant, in parallel, I have to monitor, all of these attributes, right? These are the things you kind of have to keep your eye on when I'm running this process. So I'll start by how do you do model-based control at unit operation level, and just because we have 15 minutes and I'm just picking on basically one unit operation. So this is our chromatography, right? So the first thing we did was to create a mechanistic model of chromatography. In this case, we are using something called as CADIT, which is open source software developed by the research center at Zurich by Eric von Liris. And it basically allows you to solve, which is something called as general rate model of chromatography. And what you can see on the right-hand side is the prediction, basically the output of this model, right? So the model allows you to basically get that kind of a chromatogram that where each component is going to elute, okay? So once we did that, now I'm just showing you how this model can be applied, right? So the first plot is basically showing you how we induced a deviation. So we purposely said that, okay, let us have the basic, 𝐻𝐷IC variant is increasing, right? So in the feed material, my 𝐻𝐷IC variant is increasing, and you can see that on the right-hand side that as your 𝐻𝐷IC variant increases, obviously through your process, right? Because protein A does not do anything to the acid variant, right? So whatever acid variant is increasing in the feed coming from your bioreactor, that is going to continue all the way through till you hit cation exchange chromatography, okay? And that's where basically your model will calculate. If you look at the right-hand most plot, it will basically recalculate your pooling criteria, right? So the model is taking as an input my charge distribution or charge variant distribution in the feed material. And as an output, it is calculating the pooling criteria that I ought to use, right? So you can see that the pooling criteria changes, right? And at the bottom, you can see that over many such deviations, how despite those deviations in the feed material, the output of your cation exchange chromatography step is fairly uniform as far as charge variant is concerned, okay? Similar thing, I'll just pick one more small example, single pass UFDF or SPTFF. Again, we have a mechanistic model. In this case, what I'm doing is the model, if you have varying concentration of feed material to my TFF, the model basically takes that as an input. It calculates the feed rate that you need to use, okay? And by changing that feed rate, I can get a consistent product quality basically, right? So you can see on the right-hand side, where basically, you're seeing different deviations, right? So the first is my steady state. The second is my feed rate. I have increased from 3 to 3.5. And you can see that immediately my flow rate changes from 19 to 19.4. My final concentration is 10.1, right? Deviation 2, I further go to 4. Again, my flow rate changes to 20.2 and my final concentration goes to 9.8. So essentially, your target is 10, obviously. So you are able to go to 10 plus minus, say 0.2 concentration in your output, irrespective of your concentration in the incoming fluid. So that was part one. Another area that we are working is using this AI/ML, right? So when you're doing biomanufacturing, obviously there is a lot of information that is being generated, at any given point of time, right? It's a boatload of information. And the question is, what can I get from this information that can be useful, for my process? So I'm just again giving you one example from chromatography. I'm taking in data, so on the left-hand side you can see protein A column UV to 80, cation exchange column, UV280, cation exchange conductivity, protein A, pH, right? This is data which is readily available, right? Any skid you are using will be spitting out this data. All this data is going into my AI/ML model, the structure of which is shown on the right-hand side. And you can see at the bottom that the table there, these are variables I can predict, just purely based on this data. I'm not doing any HPLC analysis, right? There's no direct measurement of any of these things. But purely based on this readily available data, I can get stuff like, what is the elute concentration in protein A? What is my acidic charge variant? What is my cation exchange elute concentration, right? Again, not everything you can get, obviously, right? Because it depends on, again, how good your model is. But remember, this is a model that we have developed in my lab, right? So we have limited data. In routine manufacturing, you'll have tons of data. So you can imagine the power of these models will only increase as you feed more and more data. Similarly, for UFDF, we have used this kind of a modeling to predict when to clean, right? Because when I'm running continuous, operation, a major issue in your membrane operation will be when do I clean this thing, right? If you don't clean, obviously you're gonna, at some point the system will just choke, right? Which will be disruptive. So the model can tell you in advance when it is time to clean and then use that cleaning regimen to keep that operation running smoothly, okay? Okay, this is the last part of my presentation. So now we are looking at how to apply this process-wide, which is obviously many times more complicated than doing unit operation based control, right? So now, and this is kind of the general structure of what we are doing. First is automation and integration. Second is real-time data analysis. So data that I'm getting, how do I analyze in real time? Real time is important if I'm doing continuous, right? Because like I said, you don't have the luxury of taking time and sitting back and reflecting on the data, right? You have to decide right then and there what I need to do. And the bottom part is obviously my control part or the decision support part, right? Because what do I do? Just looking will not do anything, right? I mean, if you have a problem, you'll just know it's a problem, right? Unless I act on it, your continuous process will still derail. So I'm just giving you some examples on how this can be managed. So essentially, we started with unit operation based control. We kind of developed control for each unit operation in the process. And now we have kind of linked them all together, right? So because ultimately, the whole process is one, right? So you have to think about process-wide control. So for example, in this case, the deviation is your protein A column fails, right? Which can happen in real life. What the action will take is it will switch loading to the standby column. It will direct the dilution to waste tank, right? Because your column failed. So whatever came out obviously is unlikely to meet your specification. So that material is discarded. And then the last point is the important part where it is like you have to compensate that mass balance for subsequent unit operations, right? Because when you discarded that, if you're doing a mass balance, right, your steady state is interrupted, right? So obviously you have less material going for the future unit operations. And that's what you see on the right-hand side. I know I have limited time, so probably not enough to decipher this, but what I'm showing you is how the consecutive steps adapt to this deviation, right? So the deviation is happening in protein A, which is my first line. The second one is showing you the cation exchange input, right? So cation exchange column I have to hold for some time because I discarded one cycle, right? That material is not there. So I have to stop my cation exchange for a little while. And the last one is showing you how you restart your cation exchange column and the process continues, right? So the question is that basically any such disruption happens, how do I keep the process going so that I'm not stopping the complete process. I'm just basically, passing the deviation through while maintaining each unit operation is still doing what it normally does, right? So the product quality is not affected, but the disruption kind of passes through that process. Another example is what if my harvest material quality changes, right? Which can happen, right? Your cell culture people did not do a good job. For whatever reason, a particular batch has, in this case, very high basic variance, right? What do you do? So you can see here again that how that model that I spoke about earlier, that model will change my cation exchange pooling decision. And then as a result of that, you will have a smaller pool, right? Because your quality of material is poorer. Obviously, you want to keep the cation exchange elution quality constant. so the amount of material will decrease, right? And for that, I would have to adjust my SPTFF flow rate, right? Because the material coming to the last step obviously will be lesser, right? So that flow rate has to be reduced so that your steady state is maintained. The last slide I think I have is that how, if the, again, your cell culture people did a really good job, right? So your titer went up. What are you going to do? Now, again, I have to actually adjust my frequency of the protein A column because, again, you have more material coming in, right? So that frequency has to be increased to deal with that material, and then how the loading, either you change the loading or the loading time, but how the deviation, and you can see in the right-hand most side, how the deviation passes through. So the deviation in cation exchange, I'm pretty much able to deal with that deviation, right? So the consecutive steps are unaffected, right? So it's all about basically, and I apologize, it's maybe too much for, a 15-minute talk, but the point is that how, you deal with deviation happening in one part of your process without disrupting the whole process, right? That's basically what it's all about. So this is kind of what we have done. So we have been doing this for almost 5 years now. So a lot of work has gone in, but we have figured out basically how to do this for the entire process from end to end. And I'll stop here just to thank IIT-Delhi, my center, CBT, and then TCS that we have collaborated with. And thank you all for your attention.